Dear students, today we'll begin the topic Young's double slit experiment. So what it deals with is basically the mutual interference of light waves. Here light is treated as waves or rays. So this is the construction of Young's double slit experiment, where there are two sources S1 and S2 which are coherent sources. This has to be coherent, otherwise this experiment will not work. So these two sources has to be coherent. So what are coherent sources? Coherent sources means two sources emitting light continuously having sharply defined phase difference which remains constant with respect to time. So the coherent sources must have same amplitude, which the coherent sources emitting light must have same amplitude, and as well as if there is a phase difference between them, then that should remain constant with respect to time. These are the two criterions of coherent sources. Now consider a screen placed at a distance d apart from the slit system. Two rays S1 from S1 and S2 meet at P and mutually interfere at P. So we want to calculate the intensity at point P, which is at a distance y from this point C. C is the foot of the perpendicular drawn from O. Now these two slit sources, which are coherent sources, are at a distance d apart. Now the path difference between these two rays S1P and S2P is basically this thing. How we have guessed that this is the path difference? We have done just like this. We have dropped a perpendicular on this ray S2P from S1. So this is the foot of this perpendicular, right? The point T. So S1T is a perpendicular drawn on S2P. So this length is basically the path difference between these two rays S1P and S2P. So after this point T, both the rays start simultaneously. Before that, there was a path difference between them. What was the path difference? This much, S2D, which is x. So this is basically written over here. You can copy that by pausing the video if you want. So here S1 and S2 are two coherent sources separated by a distance d. Let C be the foot of the perpendicular drawn from O. So point C is equidistant from S1 and S2. As because there is a midpoint, so we are just breaking this distance d into two halves, d by 2 and d by 2. Okay, so this is the foot of the perpendicular equidistant from S1 and S2, and also has the maximum intensity. As this is the central point, so here the ray must interfere and gives us a bright spot. The maximum intensity of bright spot occurs over here at this point C. Now a screen is placed at a distance d from the slit. Consider a point P over there at a distance y from C. At a distance y from C, where we want to find the intensity. Two rays S1P, S2P, starting from S1 is to reach P and interfere with each other. So this is the introduction. Now the calculation. You can copy just this. Okay? Clear? So let us just rub it and find out the path difference, which is this x. So we are just rubbing it. Okay. So we'll start with writing let x be the path difference between these two rays S1P and S2P. Between S1P and S2P. Clear? Now we'll treat these two triangles. And these two triangles are right angle triangles, right? These two triangles S1P and name them, some say MN. So we'll treat triangle S1PM and triangle S2PM. So these two triangles are right angle triangles. So we will apply the Pythagoras theorem over here. So in triangle S1PM, what we have is basically S1P square is equal to y, this much is y, this much is y, this much is d by 2. So how is this much? This is y minus d by 2. This length is y minus d by 2 gives us pm. So y minus d by 2 whole square plus this length. This is nothing but d. So this length is nothing but d. So d squared. In triangle, this triangle S2P n, we have S2P whole square is equal to this much, this square plus this square, this length square plus this length square. This is how much? This is y, this is d by 2. Y plus d by 2 gives us this length Pn. So y plus d by 2 whole square plus this much, this is d square. Now we'll just subtract these two. So S1P whole square minus S2P whole square gives us, or rather we should just change it, S2P minus S1P, as because this is longer than this one. So S2P minus S1P is y plus d by 2 whole square plus d square minus this thing, that is y minus d by 2 whole square minus d square. So this thing cancels out. Expand this. We'll get y square plus 2 into y into d by 2 plus d square by 4 minus y square plus 2 into y into d by 2 minus d square over 4. So this thing cancels, this thing also cancels. We are left with these things twice. So 2 into 2y d by 2, 1 2 gets cancelled, and we are left with 2yd. Now, what is this? A square minus b square, a plus b into a minus b. So a plus b into a minus b gives us 2yd. So how is this much? We can take S1p nearly equal to S2p. If we neglect this part difference, we can nearly take it, this is the nearly sign, is equal to this distance where the screen is apart from the slits, which is d. So this gives us d plus d, 2d. So S2p minus S1p is the x. So x is basically this thing. So this is basically x. So x is equal to 2yd over 2d. So 2 gets cancelled and we are left with yd by d. So this is the path difference. X is equal to yd by d. This is the path difference. Now from this path difference, we can get two cases, very important case, the maxima and the minima. Depending upon which, the point P will be a bright spot or a dark spot. So in the fringe, we'll see fringes. When we observe the experiment in a microscope or something lab apparatus in the spectroscope, then we'll see fringes of alternate brightness and darkness like this. So one is bright, one is dark, one is bright, one is dark, one is bright, one is dark, like this. So we have alternate brightness and darkness. So this point P will have a maxima or a minima, depending upon which P will be a bright spot or a dark spot. That will result into a constructive or a destructive integral. Every term has the same meaning. Okay, so let us find out the various cases of this path difference. So I'm running it, just not noted it down.